Hello students, myself Dr. Mahantesh K, Associate Professor, Department of Electronics and Communication Engineering, SJB Institute of Technology. Welcome you to this pre-recorded sessions on electromagnetic waves, Introduction to Electromagnetic Waves, Module 1, Class 6. Previously, we had discussed about Coulomb's law and we solved a couple of problems on electric field intensity and the force equations for multiple charges, line charges, surface charges, and volume charge density. In this video, we will be discussing more about electric flux density. Long back around 1837, the director of the Royal Society in London, Michael Faraday, was interested in static electric fields and the effect of various insulating materials on these fields. So this led to his famous invention, the electric motor. He found that if he moved a magnet through a loop of wire, an electric current flowed in the wire. The current also flowed if the loop was moved over a stationary magnet. So we can conclude that changing magnetic field produces an electric field. In his experiments, Faraday had a pair of concentric metallic spheres constructed, the outer one consisting of two hemispheres that could be firmly clamped together. He also prepared shells of insulating materials or dielectric materials which would occupy the entire volume between the concentric spheres. You could see here the outer sphere and the inner sphere of metallic conducting spheres and the inner dielectric material. Inner sphere of radius are equal to A and the outer sphere of radius are equal to B, and the inner sphere is charged with positive charges, the outer sphere with the negative charge quantities. So Faraday surprisingly found that there was a sort of charge displacement from the inner sphere to the outer sphere, which was independent of the medium. We refer to this flow of displacement or displacement flux or simply electric flux, where psi is equal to the total number of charges on the inner surface, where psi is the electric flux measured in coulombs and Q is the total charge on the inner surface, which is also measured in terms of coulombs. At the surface of the inner sphere, psi coulombs of electric flux are produced by the given charge, Q coulombs, and distributed uniformly over a surface having an area of 4 pi a square. The density of the flux at the surface is psi by 4 pi a square or Q by 4 pi a square, coulombs per meter square. The new quantity, electric flux density, is measured in terms of coulombs per meter square and denoted in capital D. And the direction of D is always at a point in the direction of the flux lines. So now the magnitude of D is given by the number of flux lines crossing a surface normal to the lines divided by the surface area. Referring again to the concentric spheres, the electric flux density is in the radial direction always. So flux is always radiating out of this sphere. So I can say D is equal to the total number of charges over 4 pi r square. The total charge over the total surface area. The total surface area of this sphere is 4 pi r square. With respect to the inner sphere, it is 4 pi a square in the direction of radius, that is AR. So with respect to the outer sphere, D at R equal to B is equal to Q by 4 pi B square in the direction of radius. At a distance R, where R is greater than A and less than B, somewhere inside the sphere, I can generalize the equation D is equal to Q by 4 pi R square normal to the radial direction. So if we make the inner surface smaller and smaller, it becomes a point. And we can refer to it as a point charge while still remaining a charge of Q. The electric flux density at a point R meters away is given by D is equal to Q by 4 pi R square in the direction AR. Comparing the previous video, the radial electric field intensity of a point charge in given free space is E is equal to Q by 4 pi epsilon naught R square AR. Therefore, in free space, the following relation applies. D is equal to epsilon naught E. For a general volume charge distribution in free space, E is equal to volume integral of rho v dv divided by 4 pi epsilon naught R square AR. Therefore, D is equal to volume integral of rho v dv 4 pi R square into AR. Why? Because epsilon naught is getting cancelled in the numerator and the denominator of electric field E. So these are a general charge, volume charge distribution in free space, and electric field and the flux density are given by the following equations. Let us now solve a simple problem on finding electric flux density at a point having a distance of 3 meters from a uniform line charge of 8 nanocoulomb per meter lying along the z-axis in free space. Electric field intensity is given by rho L by 2 pi epsilon naught R a rho. This rho is nothing but a radius. D is equal to rho L by 2 pi rho a rho. Why? Because D is equal to epsilon naught E. Therefore, substituting and solving the equation for the value rho is equal to 3 meters, that is radius is equal to 3 meters, will be obtaining D is equal to 1.273 into 10 power minus 9 by 3, which leads to 4.244 into 10 power minus 9, minus 10 a rho coulomb per meter square, nanocoulomb per meter cube. Another example of calculating D at point P of 6, 8, minus 10 produced by a uniform surface charge density with surface charge density is equal to rho s 57.2 microcoulomb per meter square on the plane x equal to 9. We know that E is equal to rho s by 2 epsilon naught. D is equal to epsilon naught E. Substituting the values of rho s and AN. So it comes around 28.6 AN microcoulomb per meter square. But at point 6, 8, minus 10, AN is equal to minus AX. Now D is given by D is equal to minus 28.6 AX microcoulomb per meter square. Thank you for watching this video. I hope you have enjoyed this video on electric flux and flux density. In the next coming videos, we'll be discussing about more on electric flux density and numericals associated with electric flux density. Thank you. Take care.